Up to this point, our oscillations have not been damped. They would go on forever. That's not physically reasonable, so we're going to introduce some damping here now and do a quick treatment of this damped oscillator and return to it later in the course and treat it with some more detail. So we're going to imagine the same sort of physical situation as before, a mass on a spring with a restoring force negative kx. We're going to add some damping. We can imagine, the block here is being dragged through some sort of viscous fluid. So the faster it's moving through the fluid, the stronger the force is going to be. The damping force, we're going to give it this form here, negative r times x dot. X dot is the velocity, and r is the damping constant, and it's in the negative direction of the force. Adding the forces and equating that to mass times acceleration gives us an equation that looks like this. It's the same equation we had before. Here's the restoring force on the spring, but now we've added a term here which is due to the damping and is proportional to the velocity. We can solve this equation using a function of this form here. I'm not going to prove it now. You can substitute this into the differential equation and work through and show that it will solve a differential equation. You can leave that as an exercise. But this is a solution to the equation. It can equally well be written as the real part of this complex exponential, because it's the cosine function here, or we can write it like this as a sum of two complex exponentials that are complex conjugate of each other. And there's a new term out the front here that we didn't have before, and that is the damping exponential. That means that as time increases, the amplitude of the oscillation here, which is a0 times e to the gamma on 2 times t, that amplitude here will decay as time increases. The decay rate here, gamma on 2, well, what's gamma? Gamma is r divided by m. The frequency of the oscillation here is nearly the same as it was before. Previously, the frequency here was given by omega squared equal to k on m. So this frequency here was root k on m. Now the frequency here is equal to omega naught squared, which is k on m, minus gamma on 2 all squared. So this frequency here is a little lower. The damping lowers the frequency a little. However, if gamma is small, and by small I mean, say, less than 10% of omega naught, if gamma is sort of 10% or less of omega naught, then these two frequencies here, for all intents and purposes, are the same. So you need quite a lot of damping before you notice a change in this frequency. The final thing to note is that this solution is only valid in the regime where gamma on 2 is less than omega naught, so the damping is sufficiently small. If the damping becomes too large, then the oscillation stops completely. You could imagine this happening, for example, if this fluid here was something really thick and gooey like honey, and you let this mass go, it's not going to oscillate slowly around the equilibrium position. It'll just go and slowly reach the equilibrium position without ever actually oscillating. So I'm going to work through an example now of a damped oscillation. This is a graph that would be given by this equation here, but we don't yet know the parameters a0, gamma, omega, and phi. So we're going to use this graph to find them, along with the initial conditions that the position starts at 2 and the velocity starts at 0. Before we go on, I'll just point out some nomenclature we often use when talking about these kinds of curves. The blue curve underneath, this is the oscillation. So this is the sinusoidal component, sometimes called the carrier, that is given by this sinusoidal function here. The red curve that traces all of the peaks of the sinusoid, that is called the envelope, and it's given by the amplitude that's multiplying the sinusoid out the front. So we have the envelope and the oscillation. Let's first find the decay rate, gamma. We can do that by looking at this amplitude out the front here and finding the time at which the amplitude has decayed by a factor of e. That will occur when this exponent here is all equal to 1, which means that the time must be equal to 2 divided by gamma. So we're starting with an amplitude of 2. It'll decay by a factor of e when it reaches 2 divided by e, that's 0.74. That occurs when time is equal to 10, which means that 2 divided by gamma must be equal to 10 seconds, or in other words, gamma is equal to 1/5 seconds to the minus 1. To find omega, we can just count 10 periods. That is 6.7 seconds, giving us a frequency of 1.5 hertz, or an angular frequency of 3 pi seconds to the minus 1. Now we know omega and gamma. we can substitute initial conditions and solve for everything else. So at time equal to 0, the position is equal to 2. So we have a0 cos phi is equal to 2, but that's not enough because we don't know a0 or cos phi. We can use the derivative of this function here at time equal to 0 and set that equal to 0 because the initial velocity is 0. And we have this equation. This can be used to solve for phi because we can take one of these terms to the other side, divide through by cosine phi, which gives us tan phi in terms of gamma and omega. Turns out that tan phi is pretty small, and we can actually use a small angle approximation here saying that phi is equal to 1 on 30 pi. And because phi is so small, we can also approximate cosine phi being roughly equal to 1, giving us an amplitude A close to 2. So finally we get that x, a function x of t, is given by this expression here, where we've solved for omega and gamma using the graph, and the initial conditions are given us the amplitude and the phase. Recognizing that this phase here is actually fairly small, we could approximate it further and say that x of t can be given by this very simple expression here. In general, in fact, it's true that if gamma is much, much less than omega, the phase and amplitude, that is a0 and phi, will not actually depend strongly on gamma at all. They'll depend on the initial position and the initial velocity, but the damping won't affect it very strongly as long as this condition is met. And that's actually what we've seen here, because without damping, when you have an initial velocity of 0, the phase is 0. And without damping, the initial amplitude would just be the initial position. Now I can do exactly the same treatment, but instead of using the cosine function, I can use, for example, this form of the solution with the exponential and its conjugate. Subbing in the initial conditions, we would get that 2 times the real part of b is equal to 2, which means that the real part of b must be equal to 1. And so, interestingly, doing it this way, the initial position straight away gives us the real component of b. Substituting in the initial velocity, we find that this must be true, which allows us to solve for the imaginary part of b. So we don't need to solve simultaneous equations in this case. The real and imaginary parts of b just pop straight out. This allows us to write down x in this form here, where now we see this complex number b out the front of our exponentials, and this is the b and its conjugate. Converting to sinusoids, we would find that x of t is equal to all of this. So we have a cosine wave here and a sine component that is very small. 2 divided by 30 pi is the amplitude compared to the amplitude here of 2. And so, as before, we can approximate by getting rid of this part here and saying it's equal to just 2 e to the negative t on 10 times cosine 3 pi t. Now, personally, I find this treatment easier because you don't have to mess around with solving tan or phi and all the rest of it, but it's, kind of a matter of taste. But I thought it's good to see both so you can see how they both work.